January 16, 1943. Portland, Oregon. Dawn breaks over a calm harbor. The SS Schenectady sits quietly at her moorings, a Liberty ship barely 10 weeks old, fresh from Kaiser's shipyards. No enemy torpedo threatens her hull. No storm batters her deck. The morning is peaceful. The water still. Then, without warning, a sound like a rifle shot splits the morning air. Within seconds, the entire vessel fractures completely in two, the hull splitting from deck to keel as if sliced by an invisible blade. Sailors scramble as bow and stern sag in opposite directions. The ship's back is broken. While tied safely to the pier, the Schenectady wasn't alone. That same winter, the SS John P. Gaines broke apart in calm seas. The SS Esso Manhattan cracked so severely her crew abandoned ship in panic. Between 1943 and 1944, more than 2,500 Liberty ships reported catastrophic structural failures. At least 19 vessels broke completely in half. 3 simply vanished at sea, disintegrating so rapidly they couldn't even send distress signals. These weren't war casualties. These were ships committing suicide. After Pearl Harbor threw America into total war, the nation needed cargo vessels desperately. Hundreds of them. Fast. Traditional shipbuilding took 8 months per vessel. The Maritime Commission couldn't wait that long. Enter Henry Kaiser, an industrialist who'd never built ships before. His promise was audacious. Mass-produced freighters constructed like automobiles, rolling off assembly lines in weeks rather than months. His Richmond shipyards employed revolutionary techniques, welding instead of riveting, prefabricated sections instead of piece-by-piece construction. Assembly line logistics borrowed from Detroit's car factories. WWII late 1942. Kaiser's yards were launching Liberty ships in an average of 42 days. The propaganda machine celebrated this industrial miracle. The SS Robert E. Peary set a record in November 1942, built in just 4 days and 15 hours. Americans cheered. Allied shipping tonnage, devastated by U-boats, finally had reinforcements pouring into the Atlantic. Then the ships started breaking. Not from torpedo damage. Not from rough seas. But spontaneously. Catastrophically. In conditions that should have been routine, naval architects were baffled. The welds looked solid. The steel met specifications. The designs came from proven British blueprints. Yet Liberty ships were fracturing like porcelain teacups. Cracks started at sharp corners, hatch openings, gun mounts, the squared-off design of the hull. Once a crack began, it raced through welded hull plates at terrifying speed, sometimes traveling the ship's full length in seconds. The Maritime Commission launched emergency investigations. Metallurgists examined steel under microscopes. Engineers reviewed stress calculations. Naval inspectors crawled through cargo holds. Everyone searched for the culprit. Bad steel, faulty welds, design flaws, inadequate quality control. Ships kept breaking while committees debated. Sailors grew terrified of their own vessels, knowing the hull beneath their feet might unzip without warning in cold Atlantic waters. The miracle of mass production had become a maritime nightmare, and nobody could explain why ships built in record time were failing in record numbers. The answer came from the least likely source, a welder on the assembly line who wasn't supposed to question engineering decisions. Bessie Hamill worked the graveyard shift at Kaiser's Richmond. Yard number 3. One of thousands of women who had flooded into shipyard work after the men shipped. Overseas. She'd been welding hull sections for 8 months, long enough to notice. Something the engineers hadn't. Every night. She watched her team weld massive steel plates in a sequence that made no mechanical sense. Welders started at the edges and worked inward. Began at one end of a seam and ran straight to the other day as each weld cooled. The metal contracted, pulling, warping the plates. She could see the stress building, the steel distorting under her torch. When welders finished one section and moved to the next, they locked that stress into the structure permanently. Her foreman dismissed her concerns. She was a welder, not an engineer. But Hamill persisted. In November 1943, she requested a meeting with yard supervisors, breaking protocol that could have gotten her fired. She brought samples, test plates welded in different sequences. Some warped badly. Others, welded from the center outward, stayed flat and true. The supervisors were skeptical. One agreed to observe the production line during Hamill's shift. What he saw confirmed everything. Welders were torturing the steel, forcing it to hold stresses it would carry for life. Every cooling weld created residual tension. Combined with cold Atlantic waters, That stress made the steel brittle, ready to crack. Hamill's insight was simple: weld from the center outward. Alternate weld locations. Avoid long, continuous runs. These weren't theories. They were practical observations from someone who felt the metal move under her torch. By December 1943, her findings reached Henry Kaiser himself. He faced a brutal choice: admit that every ship so far had flaws, or ignore a welder's claim and risk more disasters. Kaiser didn't hesitate. He ordered full tests. Results shocked everyone. Traditional welds held internal tensions over 30,000 psi. Hamill's sequence welds, just 12,000 psi. Same steel. Same welders. Only the order changed, and the difference was life or death. Metallurgists now understood: steel isn't static. It's crystalline. When welded, it expands under heat and contracts when cooling. If constrained, that contraction locks in residual stress. In near-freezing Atlantic waters, the steel's ductility vanished. It became brittle like glass when brittle steel met locked-in stress at a sharp corner. Cracks formed and propagated faster than sound through the hull. The Schenectady's fracture finally made sense. Built in winter, welded wrong, her hull carried millions of pounds of internal tension. When temperatures dropped to 28 degrees Fahrenheit, a crack started, and in seconds, the ship tore apart. Riveted ships never suffered this. Rivets acted as natural crack stoppers. Welded ships were continuous, efficient, but vulnerable. In January 1944, Kaiser made a decision that would define his legacy. He halted Liberty ship production at Richmond Yard 2 and redirected everything to a new class, the Victory ship. This was no minor modification. It was a complete redesign based on Bessie Hamill's welding observations. Kaiser's engineers rounded every square corner, redesigned hatches, and changed steel composition: less carbon, more manganese, and a touch of nickel for toughness. He retrained 90,000 shipyard workers. Hamill herself became an instructor, teaching welders how to follow precise numbered sequences: weld 1 here, 2 there. Never straight runs. Prefabrication expanded. Sections were welded under controlled conditions, then stress-relieved in ovens before final assembly. By February 1944, the first Victory ship keel was laid. Critics mocked the slower pace, but Kaiser watched the inspection reports. 0 cracks. By June, the SS Benjamin Warner was built in 5 days and 11 hours, faster than any Liberty ship, and flawless. Between June 1944 and August 1945, 531 Victory ships entered service. None suffered catastrophic hull failure. The transformation was total. Victory ships carried full loads at 15 knots through rough seas without fear. Liberty ships broke. Victory ships endured. The numbers told the story. Liberty ships cost $2 million each. 4.6% catastrophic failure rate. Victory ships, $2.6 million each. 0% failure rate by war's end, mariners said. Liberty ships were built by the mile and cut off by the yard. Victory ships were built by the inch and measured by the year. Bessie Hamill returned to civilian life quietly. No medals, no headlines. But her idea lived on. Every modern welded structure, pipelines, bridges, skyscrapers, uses her stress relief sequencing principles. The Trans-Alaska Pipeline, nuclear reactors, even the Golden Gate Bridge retrofit, all trace back to her discovery. Her lesson outlived the war. Sometimes the person closest to the work sees the truth experts miss. Sometimes slowing down to do it right is faster than doing it wrong twice. In 1943, America's ships were breaking because nobody listened to the welder. In 1944, they stopped because one industrialist did. That difference helped win the war and changed engineering forever.